we are applying the network side build. We have done the logical design and the address plan, but we still need to implement the network physically. So we need clear definition of what device connects to what device from which port, through which cable or which SFP. So all this has to be defined properly. So this is where network engineers come up with something called patch plan, where this will be handed over to the cabling vendors. Cabling vendors refer to the patch plan and make the connections as defined in that. So if you have already seen my address plan video, feel free to skip the topology section as it's the same thing. And to explain, we are looking at two offices, small office and medium office. Here is the small office physical topology. We have a single WAN router and it is connecting to the single stack switch. We have a console server for out of band management, and we have an optional lab gateway which can be enabled. Now, this is the medium office where we have redundancy in place. We have dual WAN router and dual core switch. Both are interconnected with this link. And then we have access switches, console servers, and optional lab and voice gateways which can be enabled. This is the logical topology for visualization purposes. I have defined this entire topology in the YAML file. Following the infrastructure as code principle, this is the same thing what we saw. We have a WAN router. Like, let's first look at the site type. We have, for the small site, we have a single WAN router, flow switch, console server, and wireless. Then again, for the medium side, we have the WAN, core layer, flow switch, console servers. Uh, and we have redundancy on the WAN layer and core layer. Here we are actually defining also the model. What is the model? Then what model is connecting to what model? All this is defining the site types. Then comes the connectivity, where we say where we define the roles of the device. WAN device is connecting to the switch in the case of small office, and that we can see here WAN gateway on this port through SFP is connecting to this port through this SFP, and WAN gateway to switch, similarly WAN to console server. Then we have, for the medium offices, WAN gateway to core, the interfaces, SFP modules, and media types. Everything is defined in this YAML file. Now for the demo, let's look at BGL office, which is small office in our case, and NYC office, which is the medium office. Here we have defined the floor is 1, total AP count is 12, then the stacks are 1 stack switch, and this is a small office. Similarly, in the NYC, it is a medium office. This part was used for the address plan, the subnet blocks, but these services, lab, voice, this is what we want for the patch plan. Like, these two are enabled. Then we have the floor number, what are the number of stacks here, the AP count, and the stacks here, and the AP count. Also, if you want to like, we can increase this horizontally, right? We can increase, like, if we have a building with a now another floor, maybe on 22 we have another floor, we can have the AP count, stack, devices, define everything, and our patch plan automation should be able to incorporate that extra additions which has happened. Now let me generate a patch plan for a small office. We can see how it how the output comes. Python 3 generate patch plan. I'll give the input as PGL. So the patch plan is generated here. Let me open this. And in another screen. So this is the patch plan which is generated. We can see we have the WAN gateway. It's connecting to switch through this interface on this interface. This is the switch interface, this is the WAN gateway, and this is the SFP we are using, and this is the cable. Similarly, WAN gateway to console server, we are using this. Switch to WAN gateway and switch to lab. I think this row and this row will be same. It's just inverted. So we have a visual understanding like, okay, from switch we have these two connections going to WAN and lab, and from WAN we have these connections. Everything is very defined. And from lab it was going to switch. So this section and this section, this row are inverted. Now we have the patch plan for the small office. It is very like detailed here. Any cabling calendar can actually see this and be able to patch the connections easily. Now let's look at for the NYC. So it generated the NYC patch plan. Let me open this. Now, in case of NYC, we have a lot many devices, right? We had the lab gateways, then the voice gateways. We had dual core, dual WAN. Now this is complex. This is where if a human is trying to do this repeatably for multiple sites, the chances of errors are so much. So if you are using this automation and generating, it becomes much consistent across all the repeatable sites. So from my WAN gateway, I have the connection going to these two core switches, then to WAN gateway, then I have the interface from which it is going to what interface it is going. Everything is defined. Similarly, from WAN gateway to this is again all the connections are properly defined. Like should we use Cat6 cable, OM4, multimode fiber, then on the core switch 1 to core switch 2, what all connections are going is defined. Then again lab gateway 1. Some of this will be like reverted, right? Lab gateway 1 to core switch 1, core switch 2. Similarly, you can see the same core switch 1, core switch 2, lab gateway 1. This this row and that row what we saw just now will be inverted. So this is an entire patch plan where we have generated with the help of defining the topology in the YAML and using Python. And the Python to generate it also is pretty simple. If we go to the main, we have defined the patch plan as the class, and then we start generating on a per interface basis. Yeah, this is the class. We have the generate function, and the connections for each site is checked. What are enabled, whether the lab services are enabled, voice services are enabled, then the floor context, materials, everything is defined here. The switch port connections from what port to what port is connecting. So for every link, we are going to generate the plan. Now, for example, if we look at the patch plan, we have two switches and we have this connected. Now, let's increase the switch and see if our automation can actually do that. So I'll go to NYC input. I will use this and replicate. So I will have another floor, say floor 22, and I will have the AP count to be 20. I will let the stack remain same. I will save this. That's just a suggestion. Now let me generate the NYC input again. Let me open this. Now, if I look here, I added the float 22 and this one more like couple of switches, right? Automatically, I can see the patch plan is generated for that. And if we look at the core switch part, earlier it was connected on, so 21st floor switch was connected, or switch one was connected on 22nd port. Second switch on 21st floor was connected on 23. So now the additional floor what we added, 22nd floor switch 1 is connecting to 24. And similarly 20 switch 2, 22 switch 2 is connecting to 25. Now this is scaling. If I want to keep adding the floors and switches, my patch plan generator is able to accommodate this request. This is a small good automation which can reduce the human intervention for creating the patch plan and it will be consistent across all the sites. And when you share this with your vendors, it will be easy for them to look into the splash plan and make the physical connectivity. I hope this tool was helpful. The entire code for this tool is in the GitHub. You can check the network patch plan automation. You can use this as the reference and define it for your specific organizational requirements on how you define your sites, the naming and everything. And hope you are going to use this network patch plan in your upcoming network fleets. Thanks for watching. In the next video, let's look at how we can use agentic AI skills for network operations. Thank you.